Welcome back to an Introduction to Real Analysis. We're now in Chapter 5, Section 3, at long last, the Fundamental Theorem of Calculus. So in this section, we're going to discuss and prove the Fundamental Theorem of Calculus. We consistently abbreviate this as FTC. Now, the entirety of integral calculus is built upon this theorem, hence why we call it so fundamental. The theorem relates to the seemingly unrelated concepts of integral and derivative. We're all used to seeing them presented in a calculus class, but why are they the two sort of fundamental operations and what do they have to do with one another? So it tells us how to compute the antiderivative of a function using the integral and vice versa. So here is version 1 of the fundamental theorem of calculus. Suppose capital F maps the interval from a to b into the real numbers and is continuous on that interval, including the endpoints, differentiable on the interior, so not necessarily at the endpoints. Let little f be the derivative of capital F, and suppose that it is Riemann integrable on this interval. Then, the integral from a to b of f may be computed as capital F of b minus capital F of a. So this is the version of the fundamental theorem that we all sort of are used to learning in elementary calculus courses. Let's go ahead and prove it finally. So suppose you have a partition of the interval. We're going to call it capital P, x naught through xn. Thanks to the mean value theorem, because the function capital F is continuous on each of these little intervals and differentiable on their interiors, there is a point inside each interval so that the derivative of capital F at this mysterious point in the interval from xi minus 1 to xi is equal to capital F of xi minus capital F of xi minus 1 over delta xi, the length of that interval. So now if we multiply that denominator to the other side, and remember that capital F prime is assumed to be little f, we get that little f at some interior point, ci, times delta xi is capital F of xi minus capital F of xi minus 1. Now let little mi and capital Mi be the inf and sup of f of x on this interval. Then we see that f of one particular point is in between the inf and the sup. So this quantity, aka this difference in capital F values, is in between little mi and big Mi times delta xi. So we take this inequality and we sum up over the entire partition. Now on the left, we're going to get the lower sum, and on the right, we're going to get the upper sum. But in the middle, we get a telescoping sum, right? As we move our index, we get a positive value, capital F of xi, minus, so now we have a negative 1 times capital F at the previous endpoint. So as we increase our index, these are going to cancel each other out, except, of course, the 0th and nth term. So we now have the lower sum and the upper sum act as lower and upper bounds of capital F of xn minus capital F of x naught. But remember, xn must be b, the right endpoint, and x naught must be a, the left endpoint. So capital F of b minus capital F of a is always in between the upper and lower sums for that particular partition. Now the partition was totally arbitrary. So we can take an inf on the right and a sup on the left to see that the lower and upper integral of f on the interval from a to b act as lower and upper bounds on this difference, capital F of b minus capital F of a. Since we assumed that little f was Riemann integrable, all of this becomes an equality, and the theorem is proved. All right, so fundamental theorem proved. It's actually not hard to generalize that version of the fundamental theorem to allow for the function capital F to have a finite number of points where it's not differentiable as long as it remains continuous. Now that generalization is left as exercise 5.3.3. Now this version of the fundamental theorem is used to compute the value of an integral, and for the vast majority of people, it is kind of the only way they remember how to do it. Let's suppose we know the function little f is a derivative of another function capital F. We can then find an explicit expression for the value of the integral from a to b of little f. For example, the integral from 0 to 1 of x squared is exactly equal to 1/3. X squared is continuous everywhere, so it's continuous on the interval from 0 to 1, and is therefore integrable on this interval. Also, x cubed over 3 has a derivative which is exactly equal to x squared everywhere, including on this interval. So thanks to the first form of the fundamental theorem, to compute the value of the integral from 0 to 1 of x squared, we may simply compute the value of its antiderivative at the endpoints, x cubed over 3 evaluated at 1 minus x cubed over 3 evaluated at 0. Just to remind people who haven't seen the notation in a while, This notation right here, where you have a function with a big bar on the right and an upper and lower value, means this function evaluated here minus the function evaluated there. So 1 over 3 minus 0 over 3 gives us a value of 1/3. The second form of the fundamental theorem is just as important. Now, the first form tells us if we wish to compute the value of an integral, we just need to find an antiderivative. The second form of the fundamental theorem gives us a way to solve a certain differential equation, find an antiderivative of little f, where f is a known function and we're trying to find a capital F that satisfies that differential equation. In other words, it gives us a way to define proper antiderivatives of functions. So here is version 2 of the fundamental theorem. Suppose f is Riemann integrable on an interval including its endpoints. For an x belonging to this interval, define capital F to be the integral from a to x of f of t dt. Then this new function capital F is continuous all the way from a to b, including the endpoints. And at any point where f is continuous, little f, then at those points, capital F is differentiable, and the derivative of capital F is little f. Okay. The function little f was assumed to be Riemann integrable, so it has to be bounded. So let's let capital M be an upper bound on the absolute value of f. Now suppose that x and y are 2 points in the interval. Let's let x be larger than y. Then the absolute value of f of x minus f of y is simply equal to the integral from a to x minus the integral from a to y. However, recall that you can break intervals up into pieces and treat the integral additively. So the integral from a to x is equal to the integral from a to y plus the integral from y to x. So inside the absolute value here, we simply get the integral from y to x of f of t dt. But capital F in absolute value is less than or equal to m. So the absolute value of the integral is less than or equal to this m times the length of the interval, or the absolute value of x minus y. So f is in fact Lipschitz continuous. We have just shown that capital F of x minus capital F of y is always less than or equal to a fixed constant times the absolute value of x minus y. And Lipschitz continuous functions are uniformly continuous, not just continuous. So this function capital F is in fact Lipschitz and uniformly continuous, but all we said was that it was continuous in the statement of the theorem. Now let's let little f be continuous at some point c in the interval. We now want to show that capital F isn't just continuous at c, but is in fact differentiable, and that the derivative of capital F is equal to little f. So let's let epsilon be positive. Since little f is continuous at this point c, we can pick a delta so that whenever the difference of x minus c in absolute value is less than delta, we automatically conclude that the difference in f of x minus f of c in absolute value is less than epsilon. From here, we conclude that f of x is in between f of c plus and minus epsilon. So when x is bigger than c, in other words, when x minus c is positive, we can establish the following. The integral from c to x of f of t dt, now since f of x is in between these two constants, the value of the integral is in between those two constants times the length of the interval x minus c. Since that is positive, I can divide that positive quantity over here without flipping the direction of any of our inequalities. Now, we do have to flip the inequalities if x is less than c. However, regardless, if x isn't equal to c, we obtain the following. Okay, whether these inequalities are flipped or not, once I subtract f of c over, we get that this constant times this integral minus this constant in absolute value is less than or equal to epsilon. Okay, so with this, we now just need to bring in the definition of our function capital F. So the integral from c to x is equal to the integral from a to x minus the integral from a to c, again, just using additivity of the integral on the domain. But this is capital F of x minus capital F of c, so we get this inequality right here. Now this holds for every x in the interval from c minus delta to c plus delta, where delta is a positive constant depending on the choice of epsilon based on continuity of little f. So we now have this inequality holding on a certain interval. Delta is a function of epsilon. Given a positive epsilon, there exists a delta based on the definition of continuity for the function little f. So now let's consider epsilon as a sequence 1 over n. If we set delta sub n to be the minimum of the deltas generated for 1, 1/2, 1/3 up to 1 over n, we now find an interval on which we have this inequality holding for both 1, 1/2, 1/3 all the way up to 1 over n. Now we can simply take a limit as n goes to infinity and see that this is 0 as x approaches c. As n approaches infinity, this must have to intersect down to some interval including the point c or the single point c. Either way, as x approaches c, this quantity must converge to 0. So with this quantity converging to 0, we in turn deduce that the limit as x approaches c of that ratio f of x minus f of c over x minus c must be equal to f of c, but that's exactly capital F prime of c equals c, the final conclusion of this second form of the fundamental theorem. Now this second form of the fundamental theorem still holds if we let d be an interior point of the interval from a to b, and define capital F of x to be the integral from d to x. In other words, the lower bound of integration didn't have to be little a. It could be any interior point. So that proof is left as exercise 5.3. So what happens if there's a discontinuity involved? Consider the step function little f jumps from -1 to 1 at the origin. We're going to define capital F of x to be the integral from 0 to x of little f. Now there's this convention commonly introduced in elementary calculus courses. I don't think we've actually formally stated it. If x is less than 0, we still allow writing the integral from 0 to x to simply be -1 times the integral from x to 0. So using this convention, one can quickly find that this integrating function capital F is just the absolute value. As we move to the right of the origin, we're integrating 1. As we move to the left, we're integrating -1, but we're doing it in so-called reverse order, so we get an extra multiple of -1 there. So the original function little f is discontinuous at the origin, and that's exactly where capital F, the absolute value, is not differentiable. But there's no direct converse in the fundamental theorem. So another example is to just let g of x be 0 for all non-zero values of x, and then just give g a removable discontinuity by setting g of 0 to be 1, or really anything other than 0. Then if we construct this integrating function, capital G will be 0 everywhere, which is differentiable everywhere, even at the single point where g is discontinuous. So a removable discontinuity means that a function can be made continuous by changing the value at that point. And we've already established that changing the value of a function at its single point really does not change integration at all, meaning a removable discontinuity can't possibly throw anything off, and the function little g was really just a constant 0 except for this single removable discontinuity. So a common misunderstanding of the integral for calculus students is to think of integrals whose solution can't be given in closed form as somehow deficient. If you have a problem that's assigned to you in a calculus course and you can't come up with like a little box around something and state there's the result, you think therefore it hasn't been solved. But that's not really accurate. Most integrals we write down are not computable in a closed form expression. Even some integrals that we consider in closed form are kind of cheating. So for example, let's define the natural logarithm of x to be the integral from 1 to x of 1 over t dt. This is totally well defined as long as x is positive. The function 1 over t is continuous everywhere except 0. So as long as x is positive, that area of integration, that interval of integration, does not include where this has a nice big jump. So we are integrating a perfectly continuous function as long as x is positive. Continuous functions are integrable, so this function ln of x certainly exists. And in fact, one way a computer might approximate the natural logarithm of x is to numerically approximate this integral. Now, we didn't really simplify the integral. I mean, a Calc 1 student looks at this and says, yes, the natural log of x minus the natural log of 1, there's an antiderivative. But why? All we really did was declare that since 1 over t is continuous away from 0, this integral exists, and we gave its solution a name, and we called it the natural logarithm. So we took something that we knew existed but did not have an expression for and merely invented notation for it, and we called it ln of x. Incidentally, developing the natural log and exponential functions in this way is really the main theme of the next section. So another example, assuming we have f of x equals e to the x as a positive continuous strictly increasing function, it follows that the integral from 0 to x of e to the minus t squared exists as long as x is bigger than or equal to 0, but there is no closed form solution. By closed form, I mean something you can write down in finite space with the sort of standard functions that we're used to writing down. I'm not really formally defining it. Okay, and we're not going to prove that there exists no such solution to this integral problem, but this integral is very central to the study of normal distribution in probability theory. We work with it all the time. Just because we don't have a nice little box around an answer doesn't mean it's not something we can discuss, define, and work with. Okay, so in fact, we do give it a name. We call it ERF of x to be this integral times 2 over the square root of pi. Error function is what it stands for. So, change of variables. A theorem often used in calculus to solve integrals back in your first or second time you experienced integration in a course is the change of variables theorem, which may have been called U substitution. So now we're going to prove it. So a function is called continuously differentiable, remember, if it is differentiable and the derivative is continuous. So here is the change of variables theorem. Suppose g is continuously differentiable from the interval a to b. Suppose f maps the interval c to d is continuous, and suppose that g maps the interval ab into the interval cd. In other words, the functions can be composed in a reasonable order. Then, the integral from a to b, f of g of x times g prime of x is equal to the integral from g of a to g of b, f of t dt. Can we? So let's get provenating. F, g, g prime are all continuous by assumption, therefore so is f of g times g prime. Therefore that's an integrable function, so the left side of our desired expression exists. G is continuous, therefore g of the interval from a to b is another interval. F is continuous on the interval from c to d, so it's therefore integrable on any subinterval, including g of ab, so the right side certainly exists. So now let's define capital F from the interval c to d to the reals by this integration function. Wherever g of a happens to sit in the interval from c to d, we make this integration function from g of a to y of f of t dt and call it capital F. And remember, if y happens to be less than g of a, you simply swap the order of integration by throwing a -1 out in front. That is our convention. Okay, so using the second fundamental theorem, because little f was assumed to be continuous everywhere relevant, capital F is differentiable everywhere relevant. So we can apply the chain rule. The composition capital F of g prime is capital F prime of g of x times g prime of x, but capital F prime was simply little f. So we have this equals that, and we may now integrate both sides from a to b and use the first fundamental theorem. So first, let's look at this right expression here. We are now integrating little f of g times g prime from a to b. But, as we remarked, that is simply equal to this right here. So we are integrating from a to b capital F of g prime. Thanks to the first fundamental theorem, if I can find an antiderivative of capital F of g prime, I can evaluate it at the endpoints. Well, an antiderivative of the derivative of capital F of g would just be f of g. So capital F of g evaluated at the endpoints, but that would just be f of g of b minus f of g of a. In other words, capital F evaluated at the endpoints g of a and g of b. And again, we apply the fundamental theorem version 1. Since capital F is an antiderivative of little f, capital F evaluated at g of b minus capital F of g of a is simply the integral from g of a to g of b of little f. So, thanks to the chain rule and two distinct applications of the first form of the fundamental theorem, we're done. The integral from a to b of little f of g times g prime is equal to the integral from g of a to g of b of little f. And that was the desired conclusion of theorem 5.3.5. So as an example, let's just assume the derivative of sine x is cos x. Let's use g of x equals x squared. In other words, g prime is 2x. Then, if we perform U substitution or change of variables, using our interior function as x squared, we have cosine of g of x times g prime of x over 2. So we have this extra factor of 1/2. Now, if g of x is simply x squared, from 0 to pi, we replace our bounds with g of 0 and g of root pi. But we just have that factor 1/2, and now it's just cosine of u. Okay, and we've just called it cos of t. That 1/2 factors out. Okay, we know that scalar factors go in and out of integration. So how would I integrate 0 to pi cosine? Since the derivative of sine is cosine, I can simply compute sine at the endpoints pi and 0. Both give us a 0. So we were able to compute that the integral from 0 to root pi of x times cos of x squared must be equal to 0. Now this is a fairly easy second semester calculus problem. The point is we now have proved all of the relevant steps that go into it. Okay. Do beware, however, that we do have to satisfy all the relevant hypotheses of the various fundamental theorems if you're going to apply them. So the next example demonstrates why you don't just move symbols around mindlessly. Try to remember that all of these theorems we're using have hypotheses that have to be met. So let's take a look. As our next example, let's try to integrate from -1 to 1 the natural log of the absolute value of x over x. If one simply took g of x equals log of absolute value, which derivative gives us exactly that term 1 over x, you could then attempt to do a change of variables and just replace it with g of -1 to g of 1. Now, since that was a log of an absolute value, g of -1 and g of 1 are both 0. So even though we are integrating a non-trivial function, our region of integration has no length, and we end up with a 0 here. Okay, but there are a lot of reasons why this is not a valid solution. Do try to come up with at least one. So we tried to integrate log of absolute value x over x using a u substitution with log of absolute value. But that integrand is not even defined on the entire interval from -1 to 1. So it's not even integrable. It's in fact an unbounded function from -1 to 1. G, the log of absolute value that we attempted to do our u substitution with, is not continuous on the entire domain in question. So it violates the hypotheses of our change of variables theorem. It's not even defined, in fact, when x equals 0. So G is definitely not continuously differentiable on the relevant domain. So the hypotheses of these theorems have to be satisfied to apply them. Try to keep that in mind. So let's review everything we did here. Now, the primary way we generally interact with the fundamental theorem of calculus is in this first form. If you wish to integrate little f on the interval from a to b, find an antiderivative capital F and evaluate it at the endpoints, take the difference. Back in elementary calculus, this is the typical way most students learn how to compute integrals, for very good reason. It's quite doable, and for most people who are not getting into the proof-based version of mathematics, it's completely sufficient for most applications. But the second form of the fundamental theorem is quite important for us as well. For Riemann integrable functions little f, we can define an integral function capital F to get something which is continuous and is in fact an antiderivative wherever the function little f is continuous. So the first form tells us to compute an integral if you have an antiderivative, use it. The second form is a little more abstract and says if you have a continuous function, there is an antiderivative to be found thanks to this integration function. So the second form does give us a way to define, for example, a natural logarithm as an antiderivative of 1 over x. And as I mentioned previously, the next section really dives into this approach. Change of variables, or aka u substitution, we also derived how that works. Just remember that it does have some hypotheses, so don't get too willy-nilly about how you apply it.